Hello, this is Professor Kuehn. Welcome back to my lectures on electricity, magnetism, and light. Today what I'll be doing is giving you all a brief introduction to how to carry out this week's laboratory experiment. The laboratory experiment is calculating the speed of light, and the reference is Chapter 31 in the Student's Guide to the Great Physics text. What I want to do in this lecture is just kind of walk you through what you're supposed to do for this lab experiment. So if you turn to page 393 on Maxwell's equations, and then we'll jump ahead to the location where the lab exercise is written out, and that is on page 407. This is exercise 31.6, the speed of light calculation. So I'm just going to read this first, and then I'll explain how you do this calculation. So the goal of this laboratory exercise is to calculate the speed of electromagnetic waves using previously measured values of the electrical permittivity of space, epsilon naught, and the magnetic permeability of space, mu naught. So just to give you a brief rundown, I know we haven't talked about this in lecture yet, but I'll come back and fill in the lectures during the rest of the week. So let me just remind you of the basic idea, is that we can think of light as a propagating electromagnetic wave. That is what Maxwell is going to argue. What do we mean by that? Well, let's suppose that we have a coordinate system like this. We can imagine that light is a transverse wave. So you might imagine that it's a wave going up and down like this. But what is this a wave of? Well, according to Maxwell, it's a wave of the electric field. So if I drew the electric field, let's make that blue. Everywhere in here, the electric field would be pointing upward, and right here, the electric field would be pointing downward in this direction. And right here, the electric field would be pointing upward, and down here, the electric field would be pointing downward, and likewise upward and downward. And this entire electric field wave would be traveling along the z-axis with some velocity v. Well, not only that, but if you have an electric field that also is generating a magnetic field, so I'm going to draw another wave that is oriented perpendicularly to the electric field, and this would be the wave of the magnetic field. So the electric vibration is accompanied by a magnetic field vibration, which is pointed, I guess, along the x-axis if the electric field is pointed along the y-axis, like this. So these little arrows right here are the magnetic field, B, and these little arrows here indicate the electric field, E, and this entire structure then is sliding rightward at some velocity v. And what Maxwell is going to argue is that the speed of this electromagnetic wave is equal to 1 over the square root of the magnetic permeability of a vacuum times the electrical permittivity of the vacuum. And these two quantities were quantities that we came across earlier in the semester in our measurements of Coulomb's law and the force between electrical currents. So I'll remind you about that in a moment. So we came across these before, and the idea is that by measuring the magnetic permeability mu naught and the electrical permittivity epsilon naught, one can calculate the speed of an electromagnetic light wave. Okay, so how do we arrive at these values, mu naught and epsilon naught? Well, first of all, let's deal with mu naught. So remember, we did an experiment where we had two wires. This was back earlier in the semester when we were studying the work of André-Marie Ampère. And when these were separated by a distance r, there was an electrical current I was passed through both of these. This was a current in opposite directions. When that happened, well, you got a force that was pushing these apart. Okay, and how big this force was depended on both the electrical current that was traveling through them and the distance between them. So you might recall that the force of repulsion was equal to mu naught times the product I1, I2 over 2 pi times the distance r between them. And since the currents were the same, one could just write this as mu naught times I squared over 2 pi r. In your lab, what you did was you plotted the force on one axis versus the current on the other axis, and you found that your data, you probably did some kind of curve fit, and to see whether or not this went as I squared. Another way you plotted this was you plotted force versus the distance between them. You got some data and you did a curve fit to see if this went as 1 over r. And to the extent that your data, to the extent that the force was proportional to r to the minus 1 power, and to the extent that your force was proportional to I squared, that was a validation of this, this formula that we just derived a moment ago, or wrote out a moment ago. Now, the idea is that one can use this exact same data to extract a value for mu naught. How do you do that? Well, if you plot, let's say, you can do it either way, plotting force versus current or force versus r, and treating the fitting parameter that one generates in doing this fit as a way of extracting mu naught. So let's see, if we plotted, let's say, force versus I squared, let's just do that one, you'd have mu naught over 2 pi r times I squared. And if you plotted this data, force versus current, this looks like a y equals ax squared kind of plot. So if you fit a formula y equals ax squared and extracted your value of a using a curve fit, you could then say, well, whatever a value I get is just going to be equal to mu naught over 2 pi r. And so then one can get the value of mu naught by just plugging in what the distance r was between your two wires when you were doing this experiment varying the current. So that would allow you to find mu naught by taking 2 pi times your distance r times a. That would be the way you can extract mu naught. If, on the other hand, you plotted force versus distance r, well, then you'd have to take the other parameters, the mu naught I squared over 2 pi times 1 over r. Now notice that, whoops, this is I squared, not I 2, it's I squared. Well, presumably when you're plotting force versus distance, you are keeping the current constant, and so you're plotting y equals a over r. You could fit your data to a formula like that, extract what a is, and then use that to figure out your mu naught. So you'd say a is equal to mu naught I squared over 2 pi, and solving for mu naught, you'd get mu naught equals 2 pi a over I squared, and you'd have to plug in what the constant current that you were using when you were varying the distance between your wires, and you could find mu naught in that way. Okay, so this is how you figure out mu naught. So you'll need to look back at your lab book, reanalyze your data, do a fit of your data to a function like that, and then from there extract your value of mu naught. Now what about epsilon naught? How did we find epsilon naught, or how can we find epsilon naught? Well, remember you did another experiment during maybe the second week of class where you were measuring the force between two charged spheres, right? So you took these two spheres and they were being separated by a distance. I'll go ahead and do this in orange. The distance between them was r. That's the distance between the centers of the spheres. And then you used a Coulomb balance to measure the amount of force of repulsion between these two spheres. And if these obeyed Coulomb's law, then the force should be 1 over 4 pi epsilon naught q1 q2 over r squared, and r is the distance between them. So by measuring the force between them, and by knowing the charges, and by knowing the distance, one can extract epsilon naught in a similar way that one extracted mu naught in the previous formulas. So you could plot force versus charge, and let me just rewrite this. Force equals 1 over 4 pi epsilon naught q squared over r squared, because we're using the same charge. You could plot force versus distance, and if you know the charge, then you can figure out epsilon naught, or you could plot force versus charge, and if you know the distance, you could find epsilon naught. Now there's one difficulty here that didn't show up in the other one, and that is that you don't know directly what the charge is on each sphere. All you know is the voltage of the power supply that you used in order to charge up those two spheres. You don't know what the charge is. Well, you might say to yourself, wait, we did find out what the charge was, and we used the capacitance of those spheres. So you remember that the charge on a charged up object is the capacitance of that object times the voltage we used to charge it. So you can calculate the charge from the voltage. So you might have in your lab book written down, I used 3,000 volts or 4,000 volts or 5,000 volts. You multiply it by the capacitance of the sphere and you get the charge. Fair enough. But how do you know the capacitance of the sphere? Well, remember the capacitance was 4 pi epsilon naught times r, where r is the radius, in this case, the radius, I guess it would be from the center of the sphere right here. That's our capital R. Notice it's not the same thing as little r. That's the radius of the sphere. Now, it should dawn on you right now that there's a problem, because we measured the radius of the sphere and we used epsilon naught to find the capacitance. And the whole point of this lab is to find epsilon naught, or at least as part of the lab, we need to determine epsilon naught. So we can't use epsilon naught to find epsilon naught. So that's a problem. So we don't really know the capacitance of these spheres, hence we don't know how much charge is on them. That's a problem. Well, what we could do is we could go back and rewrite our formula. Force equals 1 over 4 pi epsilon naught. And then for charge, we could put the capacitance times the voltage. So we could put 4 pi epsilon naught R, that's the capacitance, times the voltage, V. So that is Q squared over R squared. So I basically just used this formula right here and plugged Q equals CV in for Q, and I plugged the capacitance in for C, and now we have a formula that looks like that. Well, the nice thing now is we can rearrange this formula. You've got 4 pi epsilon naught squared over 4 pi epsilon naught, so that leaves you with 4 pi epsilon naught in the numerator. And you've got r squared, remember that's the radius of the sphere, squared. You've got v squared, and you've got little r squared. So now, here we have it. We have a new formula that relates the force of repulsion between these spheres to the voltage you're using to charge them up, the distance between them, and the radius of the spheres. So now, notice what we can do. We can extract epsilon naught, because we can plot force, for example, versus voltage. And if we did that, we'd take 4 pi epsilon naught capital R squared over little r squared times v squared. And now notice you can plot y equals ax squared, where the voltage is on your x-axis, the force is on your y-axis, and this fitting parameter a is then this quantity in parentheses. So you can identify your fitting parameter with 4 pi epsilon naught capital R squared over little r squared. And if you know the radius of your sphere and you know the distance between them as you are varying the voltages, you could figure out epsilon naught. And hence we have a way to find epsilon naught from our Coulomb balance experiment. And now once we know epsilon naught and mu naught, we can plug those into this formula right here to find out what the calculated speed of light is. And what Maxwell did is, using data like this from the force between charged spheres and the force between electrical currents, he was able to calculate the speed of light, the speed of these electromagnetic waves, and he noticed that the speed of these electromagnetic waves happened to be very close to the measured speed of light. Hence, perhaps light is in fact a traveling electromagnetic wave. I want to emphasize once again how peculiar this is. Notice that what we're doing is we're taking two experiments that have nothing, seemingly, to do with light. We're doing one experiment measuring the force between two charged spheres. We're doing another experiment that is the force between two current-carrying wires. And by doing these two seemingly unrelated experiments, one gets information about the speed that light travels through a vacuum. And the way that Maxwell might understand this is that the two experiments that we were doing were telling us something about the properties of space. So if you look at Coulomb's law, it relates the force between charges to the magnitude of the charges, the distance between them, and some property of space, epsilon naught, called the electrical permittivity of space. That tells you something about the nature of the space separating those two charges. Also look at the formula for the forces between currents. It tells you how a magnetic force, that is a force between two current-carrying wires, is transmitted through space. So if we have two wires, each with a current I, separated by a distance r, they exert a force on each other, and the ability to do that depends on some property of space, mu naught. And what Maxwell is then arguing is that these properties of space, epsilon naught and mu naught, are what governs the propagation of light through space. Okay, I hope that gets you started on carrying out these experiments, or rather carrying out these calculations. You should already have all the data you need in your lab book, and so this week you're strictly working on reanalysis and calculation. Make sure you write out your calculations in your lab book and show me exactly how you're doing these before you scan in your lab report and upload it to the course management system.